All right, in this section we're going to introduce a little bit of probability. And generally, probability is an area of mathematics that tries to answer the question, what are the chances that a certain event will happen? So we're going to define some terms at first. And first, the term experiment is generally left undefined, except that it has to satisfy the following conditions. It's something that has to produce more than one outcome. More than one thing has to be possible. The outcome is uncertain. We don't know what's going to happen. The finite set of all of its outcomes can be determined prior to the performance of the experiment. So think of the experiment where I roll a die. I know that I'm either going to get a 1, 2, 3, 4, 5, or 6, right? So I can determine what the possible outcomes are first. And then we can repeat that experiment under the same conditions. The sample space is the set of all possible outcomes, and an event is just any subset of that sample space. And now we can define probability. So let's suppose we have a sample space. Think of the sample space, by the way, this is sort of like the universal set for the experiment, right? And it's all things under consideration. So suppose I've got some sample space, which we usually call S, and A is some event. So A is a subset of S. The probability is the size of A divided by the size of S, and we think of this as the number of ways A can happen divided by the total number of outcomes. So for example, suppose I roll 2 dice and I want to know what is the probability of getting a sum equal to 6. From the counting stuff that we've done, we already know if I'm rolling 2 dice, I know that the size of the sample space is 36, 6 ways for each die to come up. And we want to get a sum of 6. So let's let our event A be that we get a sum of 6. And let's write out the ways that can happen. I can get a 1 and a 5, or a 5 and a 1. I can get a 2 and a 4, or a 4 and a 2, and then I could also get double 3s. All right, so those are all the ways to get a sum of 6. So the size of A is equal to 5, and that means that P of A, probability of A, is 5 over 36. Theorem 3.7 tells us that if A and B are disjoint sets of outcomes of an experiment, then the probability of A union B is equal to the probability of A plus the probability of B. We're going to be able to prove this. It's pretty simple, actually, using what we already know about counting. For starters, actually, just to get us, before we do that, the probability of A union B, this is the same as when we talk about the probability of A or B. Remember, union is an or, and in probability problems we see a lot of sort of common language used sometimes instead of the mathematical notation. So an or is the union, and if A and B are disjoint sets of outcomes, meaning they have nothing in common, in probability speak, we would say that A and B are mutually exclusive, like they can't both happen at the same time. So if they can't both happen at the same time, right, there's no overlapping, then the probability of A union B is just the probability of the sum of their probabilities. So it'll take very little work to show this. We know from the definition of the probability that this is the number of ways that A union B can happen, or the size of the set A union B, divided by the size of the sample space. And we know this from counting before, that if A and B are disjoint, then the size of A union B is the size of A plus the size of B. There's no intersection to subtract off. And now I'm just going to do some algebra. I'm going to split it up over the addition up here. So this is the size of A over the size of S plus the size of B over the size of S. And this is equal to the probability of A plus the probability of B. There we go. Some more results down here. We'll prove the first three of these, and it won't take that long. They're actually pretty simple to prove. So suppose S is a sample space, and we have an event A and an A complement. We're going to use that same notation. That's the complement of A, so that's the event that A does not happen. The following are true. So the first is that P of S is equal to 1, the probability of the sample space itself. This is actually almost proves itself. Probability of S, by definition, is the size of S over the size of S, and that definitely has to be equal to 1. The second part is that the probability of A complement is 1 minus the probability of A. So the first thing I'm going to do is use the previous result. I know that 1 is equal to the probability of S. Now that sample space I'm going to write as a disjoint union. I'm just going to write S as equal to A union A complement. And we'll just note these are disjoint, right? A either happens or it doesn't. And it can't happen and not happen at the same time. And using the result that we proved at the top of the page, this has got to be P of A plus P of A complement. Now, let's extract part of this equation. So we know that P of A plus P of A complement is equal to 1. And we'll just subtract P of A, and we find that P of A complement is equal to 1 minus P of A. That's a particularly useful result. Because sometimes if we might be looking for the probability of an event, and it might be easier to find the probability of its complement. Just like in some of the counting problems, it was easier to count the ways that something doesn't happen. We'll find this result to be useful at times. And then the third result, the probability of the empty set. The probability that nothing happens is 0. And this just follows directly from the definition of probability. So it's going to be the size of the empty set divided by the size of S, which is 0, divided by the size of S, which is, of course, 0. So we'll leave the last two unproven. They might be in the exercises, but I think they at least pass the I believe it test, which is that for any event, the probability that A occurs is between 0 and 1, right? So it's anywhere from 0 to 100% that A happens. And then if A is a subset of B, then the probability of A is less than or equal to the probability of B. So it's like a smaller set of outcomes. And that's actually pretty simple to prove. So I'm going to leave those two unproven. You might establish those for your own amusement. Okay, so our next example, suppose we roll a couple of dice. We want to know what's the probability that the sum is not 7. So let's say we define the event. If this is our event is that the sum is not 7. That means that A complement is the event that the sum is 7. And it's a lot easier to count up the number of ways to get a sum equal to 7. I can get a 1 and a 6, or a 6 and a 1. I can get a 2 and a 5, or a 5 and a 2. I can get a 3 and a 4, or a 4 and a 3, and I'm pretty sure that's all of it. So the size of a complement is 6. That means that probability of a complement is 6 over 36, which is 1 out of 6. And so the probability of A is 1 minus the probability of A complement, 1 minus 1/6 is 5/6. Next, we have a theorem that's actually pretty similar to one of our counting theorems, or almost like very similar, stemming directly from that. If we want to find the probability of A union B, and we don't know, like they might not be mutually exclusive, then we find that probability by adding the two probabilities together and subtracting the probability of their intersection. And this is basically the same idea as when we were doing the counting, right? Say I have this Venn diagram. Right, if I count up the number of ways A can happen and then I add to that the number of ways B can happen, we end up double counting this stuff in the middle. I'm going to sort of show this in a slightly more rigorous way. So first, we'll just note that I could write A as a union of disjoint sets, and that is, it's A set minus B unioned with A intersect B. So A set minus B, that's this part right here, right? I take A and then I throw out B, and then I add in the intersection. Those two bits that are shaded right now, that's what we have written here. And then similarly, B is the set B set minus A, that's the right-hand crescent right here that I'm shading in green, union with the intersection. And with this, I can write A union B as a union of disjoint sets. I'm going to not double count the intersection. This is A set minus B, union A intersect B, union B intersect A. Sorry, not B intersect A, B set minus A, rather. So this is a disjoint union, or a union of disjoint sets. And that will come in handy. So on the one hand, actually that's a union of disjoint sets, and that's a union of disjoint sets as well. So we're going to use this fact in the theorem, what was it? Theorem 3.7. So we'll note that P of A is P of A intersect B, A set minus B plus the probability of A intersect B. And similarly, the probability of B is equal to the probability of B set minus A plus the probability of A intersect B. Now I'm going to take this line here for the A union B, and again apply that same theorem. Because that's a union of disjoint sets, I know that the probability of A union B is probability of A set minus B plus the probability of A intersect B plus the probability of B set minus A. Next, I'm going to take each of these guys here. I'm going to add them together. P of A plus P of B is P of A set minus B plus P of A intersect B plus P of B minus B set minus A plus P of A intersect B. Now take a look at what we've got here. This piece is exactly what we have up here, right? That is P of A union B. So we know that P of A plus P of B is equal to P of A union B plus P of A intersect B. And now the only thing we need to do is subtract probability of A intersect B. And we find that P of A plus P of B minus P of A intersect B is equal to P of A union B, as desired. All right, let's do a problem. We're going to find the probability that if a license plate with 3 letters and 3 digits is selected at random, the 3 letters will be the same or the 3 numbers will be the same. So, right away, what I pick up on is this or. I know that I'm looking at a union. And I'll just define these 2 events. A will be the event that the 3 letters are the same. And B will be the event that the 3 numbers will be the same. And what we want is P of A union B, which is P of A plus P of B minus P of A intersect B. So now what we've done is sort of broken this down into 3 smaller problems. I can just focus on finding P of A, then finding P of B, and P of A intersect B. So our sample space, that'll be important here, is going to be all license plates with 3 letters and 3 digits. So the size of the sample space, now we can repeat letters, like it's okay to have AAA as the 3 letters on the plate. So we are selecting with repetition both letters and digits, and using the multiplication counting principle, that means that the size of the sample space will be 26 cubed times 10 cubed. Now, let's think about the size of A and the size of B, and also the size of the intersection. So the size of A, that's the event that the 3 letters will be the same. So there can be only 1 letter that I pick. There's 26 ways to choose that letter. But once I've chosen it, I can't choose any other letters. But I can choose any numbers I want. So that'll be 26 times 10 cubed. The size of B, now I have 3 letters to pick. 3, they could be all different, they could be all the same, but like there's no restrictions. So the number of ways to pick the 3 letters is 26 cubed. And now we're going to multiply that by the number of ways to pick the digits, but there's only 1 digit, there's only 1 number that I'm using, so there's 10 ways to choose that. And now finally, for the size of the intersection, that means that the 3 letters are the same and the 3 numbers are going to be the same. So I've got 26 ways to choose that 1 letter that I'm going to use. I've got 10 ways to choose that 1 number that I'm going to use. And we multiply those together. Now let's use our formula. So each of these probabilities is just the size of the set over the size of the sample space. So we have 26 times 10 cubed over 26 cubed times 10 cubed. P of B will be 26 cubed times 10 over 26 cubed times 10 cubed minus 26 times 10 over 26 cubed times 10 cubed. Now rather than reducing each of the fractions, I'm actually just going to, since they already have a common denominator, I'm going to bring that down. And I'm going to throw this in the calculator. Okay, so up top. And divided by, I'm going to put the denominator in parentheses. I get this decimal. I'm going to see if I can't get a fraction out of that. 31 over 2,704. So there it is as an exact value. It's okay to approximate, and we get 0.0115. So there's a little bit of probability, how we can use our counting skills that we've been building to compute probability of some events.